Have you ever had one tiny decision or unexpected event completely change the course of your day? Maybe spilling coffee on your shirt or taking a different route to work sets off a cascade of events. It might sound insignificant at first, but what if those tiny shifts could lead to far bigger consequences down the line? This is the idea behind the famous butterfly effect. It's not just a catchy phrase, it captures a deep truth about how the world works. In chaos theory, that butterfly wingbeat metaphor represents the fact that even very small changes in a system can eventually unleash large, unpredictable ripple effects. Imagine a world where predictability is an illusion, where every tiny variable holds the power to change the big picture. That may sound like science fiction, but this is exactly the realm of chaos theory. Chaos theory is the field of mathematics and science that studies complex systems which are deterministic. They follow precise rules, yet extremely sensitive to their starting conditions. In other words, these systems aren't random, they are simply very hard to predict. To clarify, chaos theory doesn't mean randomness. As one science explainer notes, chaotic systems are not totally random but still cannot be easily predicted. Two almost identical starting points can diverge into wildly different outcomes, meaning our usual intuitions about cause and effect can completely break down. The concept was famously illustrated by Edward Lorenz in the 1960s. Lorenz was a meteorologist using an early computer to simulate weather. One day he ran a simulation twice with nearly identical inputs. The difference was so small he rounded one number to 0.506 instead of 0.506127. Yet the resulting forecast turned out completely different. Lorenz realized that seemingly insignificant factors can have a huge effect on the overall outcome. This discovery effectively founded chaos theory. Lorenz later posed the evocative question: could the flap of a butterfly's wings in Brazil set off a tornado in Texas? In reality, one butterfly won't summon a storm, but the metaphor highlights the sensitivity. Tiny, unmeasured influences can compound over time to produce massive differences in a chaotic system. This phenomenon is known as sensitive dependence on initial conditions. No amount of tiny tweaks or hidden precision can overcome it in the long run. One of the clearest real-world illustrations is weather forecasting. Here we see Hurricane Ian as captured by satellite in 2022. Even with all our technology, chaos in the atmosphere limits how far ahead we can reliably predict its path. Researchers note that slight differences in today's weather may evolve to become large differences in future weather patterns. In practical terms, this means that tiny uncertainties in current measurements, like a barely measured wind gust or a slight change in temperature, can grow over days and weeks until the forecast is completely wrong. Forecasters often give accurate predictions for the next few days, but beyond about a week, those predictions tend to break down because the weather is so sensitive to initial conditions. Forecasts tend to be accurate only a few days ahead. Beyond about a week, the butterfly effect kicks in and makes accurate long-range forecasting effectively impossible. Climate change may be making this even worse. A 2021 Stanford study found that as global temperatures rise, chaos in weather models intensifies. Each few degrees of warming effectively knocks about a day off the horizon of reliable forecasts. As lead author Aditi Shashadri explains, cooler climates seem to be inherently more predictable. In short, a hotter world makes weather even more erratic. That means the climate crisis could push reliable forecasting further out of reach, a stark reminder that chaotic dynamics underlie our climate system as well. Chaos isn't limited to the sky. Financial markets are another prime example of complex, unpredictable systems. On paper, markets follow economic rules and trends, but in practice, they can behave erratically. For example, one unexpected news headline or a large trade by an algorithm can trigger a wave of activity. Investors react to that, triggering others, and soon the whole market may swing wildly. Some analysts even apply the fractal market hypothesis. They use chaos theory to explain how price movements can repeat patterns across different timescales. In any case, chaos theory helps explain how seemingly healthy financial markets can suffer sudden shocks and crashes. Because so many participants influence each other, a small trigger can cascade into a big swing. By the time prices move, turbulence is already underway. No wonder we hear about flash crashes and unpredictable volatility. Chaos is always at work in the markets. Everyday life has its own chaotic elements too. Think about your commute. Leaving your house just 5 minutes later might cause you to miss a green light, which makes you hit traffic, and suddenly your entire schedule shifts. Traffic is essentially a chaotic flow of vehicles. Each driver's tiny decision ripples through the network. In biology, chaos shows up in population dynamics. A slight change in birth rates or food supply can eventually lead to wildly different outcomes for an ecosystem. Even personal choices can have chaotic consequences. A minor detour might save you from an accident or cause you to miss something important. No matter how well we plan, living systems often misbehave in surprising ways. Physicists often demonstrate chaos with a double pendulum. Two pendulums attached end to end. It follows simple physics, yet if you start two nearly identical double pendulums just a hair apart, after a few swings their motion will appear completely different. it's a mechanical demonstration of chaos. The point is that in complex, nonlinear systems, small changes can eventually produce huge differences. We might not see every link in the cause and effect chain because it's tangled up in feedback loops and interactions that multiply unpredictably. Our intuition about linear cause and effect simply doesn't apply cleanly in chaotic systems. This inherent chaos means that simply collecting more data or building bigger computers won't solve the problem of prediction. The issue is precision, not just quantity of data. Researchers note that in a chaotic system, no detail is too small to ignore. Any tiny uncertainty or unmeasured factor will grow over time and eventually dominate the outcome. Even a hypothetical supercomputer with infinite capacity couldn't guarantee the future unless it knew every tiny detail perfectly. In practice, weather models and others use ensemble methods to grapple with chaos. They run many simulations with slightly varied inputs. If all the model runs agree on an outcome, forecasters gain confidence. If they diverge, that signals high uncertainty and the limits of predictability have been reached. This image shows the famous Lorenz attractor, discovered by Edward Lorenz himself. Even though the orange line moves in a seemingly random fashion, it never crosses itself and always stays within the looping, butterfly-shaped curves. Those curves form the attractor, a hidden pattern or shape that the chaotic system tends to follow. Think of it like a leaf swirling in a turbulent stream. The leaf's exact path is unpredictable, but it never drifts entirely away from the riverbank. In chaotic weather models, for example, storm clouds may shift unpredictably, but they remain bound by an underlying attractor pattern. As one science explainer notes, a rubber ducky in the ocean will be drawn to its attractor, the ocean surface. No matter how waves and winds jostle the toy, the surface constrains its motion. Strange attractors like these reveal the hidden order behind chaos. They show that even though individual outcomes are unpredictable, the system's overall state stays within an elegant geometric shape. Another fascinating concept is fractals. Fractals are shapes whose parts resemble the whole. Chaos and fractals go hand in hand. Many chaotic processes generate fractal patterns. A small piece of a fractal looks like the entire pattern. You see fractals in nature, the branching of trees, the structure of snowflakes, the coastline's jagged outline. And these often arise from simple iterative rules. Some researchers even apply fractal concepts to markets, noting that price charts can exhibit similar patterns at different scales. Recognizing fractals in chaotic systems helps us visualize how simple mathematics can produce infinitely complex beauty. It's a reminder that chaos isn't just random clutter. It often has hidden, repeating order at every level. Indeed, even the famous Mandelbrot set, an iconic fractal, shows how endless complexity can emerge from a simple mathematical rule. Artists and mathematicians have even created fractal art using chaotic equations, turning these abstract patterns into stunning visual forms. In many cases, chaos emerges from simplicity. Iterating just a simple formula or reshaping a geometric pattern over and over can yield highly complex fractal patterns that no one could have predicted by looking at the original rule. So what do we do with this knowledge? One lesson of chaos theory is to embrace uncertainty and build resilience. Scientists and planners already do this in various ways. Meteorologists, for example, use ensemble forecasts and focus on probability ranges. If model runs disagree, they issue forecasts that emphasize uncertainty instead of a single number. Businesses and governments often develop multiple scenarios for the future rather than betting on one outcome. On a personal level, chaos theory suggests we should have backup plans. In finance, that means diversifying investments. In daily life, it means expecting the unexpected and staying adaptable. Carrying an umbrella, just in case, or having an extra route planned for a trip are simple examples of resilience in the face of chaos. Chaos theory also promotes flexibility and risk management. Companies know that small market shifts or random events can drastically change outcomes, so they diversify products, hedge against risks, and prepare contingency plans. Similarly, emergency services prepare for many possible disasters, knowing that a tiny trigger could escalate unpredictably.
Don't try to drain my energy, the enemy is everything. It's mentally, unhealthily, spreading like a rare disease. But I won't let it get to me, I don't need your therapy. I can leave a legacy of leading by intensity. Come on, we can fight this, freedom is priceless. Spread just like a virus.
Chaos theory is both humbling and enlightening. It's humbling because it shows a fundamental limit to prediction. No matter how sophisticated our tools, complex systems will always keep some secrets. But it's also enlightening because it reveals hidden patterns in apparent randomness. Once we accept that weather, markets, and even our own decisions can behave chaotically, we stop being surprised by the unexpected and start seeing it as part of the system. In fact, even in our personal lives, chaos theory applies. Career counselors sometimes talk about the chaos theory of careers, meaning that small choices or chance encounters can lead to dramatically different life paths. Recognizing this encourages staying open to new opportunities and flexibility rather than rigid plans. In 2025 and beyond, chaos theory continues to inform research across fields, from climate science and ecology to economics and technology. It reminds us that trying to control everything is futile and that uncertainty is built into the fabric of reality. So the next time you wonder why the future is so hard to foresee, remember, a butterfly's wing beat or any small action might be the start of a chain reaction. Chaos theory shows that our world is a complex dance, unpredictable in detail but governed by deep mathematical rules and hidden order. That knowledge can help us navigate uncertainty with wisdom and humility,